Welcome, everyone. Today, we're diving into a crucial topic in electrical circuits: Kirchhoff's rules. As we know, circuits in real life are often more intricate than just simple series or parallel combinations of resistors. While those simpler cases helped us grasp foundational concepts, they fall short when electrical components are connected in complicated networks. That's where Kirchhoff's rules come into play. They are powerful tools based on key physical principles, specifically the conservation of electric charge and energy, that let us analyze any circuit, no matter how complex. With these rules, we can systematically find the currents flowing through every component and determine the potential differences across them. Think of Kirchhoff's rules as a universal language for circuit analysis, allowing us to unravel any electric labyrinth. This lesson will establish the fundamentals of these rules, preparing you to tackle a huge variety of circuit problems. We will build from the basic physical ideas to practical applications, focusing on clarity and understanding. So let's begin with why and how these rules work and what they mean physically. This foundation is essential before moving on to applying these to specific circuits in the next few slides. Before applying Kirchhoff's rules, it is crucial to carefully label the currents and voltages in the circuit. Imagine you have a network with many resistors and power sources. We begin by assigning a symbol for the current, like I, to every resistor branch. Along with the symbol, we draw an arrow to indicate the assumed direction of the current. This arrow is a hypothesis. If the math shows I is positive, the current truly flows that way. But if I comes out negative, that tells us the current actually flows in the exact opposite direction of our arrow. This is a key idea. Our initial current direction guesses help us write equations, but the final solution reveals the true directions. Next, for each cell or battery, we indicate its positive P and negative N terminals. The potential difference between these points is given by V equals V of P minus V of N equals epsilon minus IR, where epsilon is the electromotive force and R is the internal resistance of the cell. This formula captures that the voltage output of a battery decreases slightly due to internal resistance when current flows. If we assumed the current direction differently, we use V equals epsilon plus IR instead, ensuring correctness based on the polarity and current direction. Labeling systematically like this sets up a clear framework for applying Kirchhoff's rules without ambiguity or sign errors. Proper labels keep track of all electrical variables and make the work manageable as complexity grows. With this setup, we're ready to explore the two fundamental Kirchhoff's rules next. Let's start with Kirchhoff's first rule, often called the junction rule. At any point in an electric circuit where multiple branches meet, known as a junction or node, the sum of all currents flowing into that point must equal the sum of all currents flowing out. This rule is deeply rooted in the physical principle of conservation of electric charge. Since current represents charge flow per unit time, if charge were to somehow pile up at a junction, the current flow to that point wouldn't be steady. But in reality, steady currents mean there is no charge buildup. Whatever charges arrive must leave. So mathematically, the junction rule says that the algebraic sum of currents at a node is zero, or the currents in equal currents out. This idea is simple but powerful, helping us relate unknown branch currents by expressing how they split or combine at nodes. The image here shows currents labeled I1, I2, and I3 meeting at a junction point A. The junction rule here would be expressed as I3 equals I1 plus I2, meaning the current I3 enters the junction and splits into I1 and I2 leaving it. Notice that this rule applies to any junction or even a single point along a conductor. By applying this consistently at all junctions in a network, we reduce the number of unknowns and build the system of equations we need to find all currents. Later, we'll use these relations along with voltage rules to fully solve circuits. Next is Kirchhoff's second rule, known as the loop or voltage rule. This states that the algebraic sum of all changes in electric potential around any closed loop in a circuit must be zero. Physically, this stems from the fact that electric potential is a single-valued function of position. If you imagine starting at any point in the circuit and moving all the way around a closed loop back to that point, you must end up at the same electric potential you started from. Therefore, adding up all voltage increases and drops along the way must balance out to zero. When moving through a resistor, this change in potential is a voltage drop calculated by Ohm's law as the product of current and resistance, IR. When traversing a battery or cell, voltage changes correspond to the electromotive force and any internal resistance effects, which we described earlier with the V equals epsilon minus IR formula. In the same circuit diagram from the last slide, loops are shown where we apply this rule by summing voltages. For example, in one loop you consider voltage drops across resistors and voltage gains from batteries. By applying the loop rule to each independent loop in the network, we obtain equations that relate the unknown currents and voltages. Together with the junction rule, these form a complete set of equations to solve complex circuits. Physically, the loop rule is an expression of energy conservation. Electrical energy gained and lost around a loop must net out. Let's see how Kirchhoff's rules come to life in a real circuit example. Here is a circuit with several resistors of different values and two voltage sources, a 45-volt and an 80-volt battery, connected at various points. Currents in different branches are labeled as I1, I2, and I3, with arrows indicating their assumed flow directions. By applying the junction rule at node A, where the current I3 splits, we derive the relation I3 equals I1 plus I2. This means all current entering the junction by I3 splits into two paths, represented by I1 and I2. Next, to find the values of these currents, we apply Kirchhoff's loop rule to two different closed loops within this network. The first loop yields the equation -30 I1 minus 41. I3 plus 45 volts equals 0, representing voltage drops across resistors and the voltage rise from the battery. The second loop yields another equation relating I1 and I2 currents, resistor voltage drops, and the 80-volt source. These two loop equations, together with the junction relation, form a system of simultaneous equations. By solving these equations, we can find numerical values for the currents I1, I2, and I3, fully describing the current flow in the circuit. This example highlights how systematic application of Kirchhoff's rules and careful current labeling allow us to decode any electrical network. Up next, we'll use symmetry and Kirchhoff's rules in a cube resistor network example to deepen understanding. Now, let's examine an interesting example involving a cubical network of resistors. The cube has 12 edges, each with a resistor of 1 ohm. A 10-volt battery is connected between two opposite corners of the cube diagonally. This network is too complex for simple series parallel reduction. But thanks to its symmetry and Kirchhoff's rules, we can analyze it effectively. Due to symmetry, currents flowing through certain edges are equal, simplifying our unknowns. For loops in this network, applying Kirchhoff's voltage law yields the relation between EMF epsilon, current I, and resistance R as epsilon equals 5/2 IR. From this, the equivalent resistance of the entire cube, as seen by the battery, is calculated as rec equals epsilon divided by 3 times I, which simplifies to 5/6 times R, or 5/6 ohms. Knowing this lets us determine the total current supplied by the battery. Then, related currents for each edge of the cube can be expressed as multiples or fractions of I, such as I/2, or 3I. This example beautifully demonstrates how Kirchhoff's rules, along with symmetry, simplify what seems like a daunting network problem. Next, we'll explore a more general circuit without symmetry, showing the universal power of Kirchhoff's rules. While symmetry can simplify circuit analysis, most electrical networks do not have such neat patterns. In these general complex networks, Kirchhoff's rules provide a systematic approach. We start by labeling each branch with an unknown current and an assumed direction. Then, by applying the junction rule at every node, we relate the currents at that node, reducing the total number of unknowns. Next, we identify independent closed loops in the circuit loops that don't overlap completely and write down loop equations derived from Kirchhoff's voltage rule for each. This yields one voltage equation per independent loop. The key is to have as many independent equations as there are unknown currents to solve the system. These simultaneous equations, often linear, can be solved by algebraic methods or matrix operations, like substitution or determinants. This approach is universally applicable, whether for simple or highly complex circuits, ensuring that Kirchhoff's rules remain fundamental tools in circuit analysis. The next slide will take you through a real example applying this full method to find branch currents in a multi-loop circuit. Let's solidify your understanding by analyzing a multi-loop circuit. Consider this network with 4 nodes labeled A, B, C, and D. It contains resistors with resistances like 4 ohms, 1 ohm, 2 ohms, and 20 ohms, plus 2 battery sources of 10 volts and 5 volts. We assign unknown currents I1, I2, and I3 with arrows indicating assumed flow directions in the network's branches. Applying Kirchhoff's junction rule at nodes establishes current relations, reducing the number of unknowns. Then, we identify 3 independent loops for applying the voltage rule: loop A, D, C, A, loop A, B, C, A, and loop B, C, D, E, B. Using Kirchhoff's voltage law for each loop, we sum voltage rises and drops. For instance, in loop ADCA, this yields the equation 7I1 minus 6I2 minus 2I3 equals 10 volts. Similarly, the other 2 loops provide their respective linear equations. Together, these 3 simultaneous equations in 3 unknowns can be solved algebraically or with matrices to find the currents I1, I2, and I3. This example exemplifies how systematic use of the rules turns a complex mesh into manageable math. Checking the solution with the junction and loop rules confirms consistency. Next, we'll discuss common mistakes students make when applying these rules and how to avoid them. Before concluding our study on Kirchhoff's rules, it's important to address some common student misconceptions that often cause confusion. First, many students believe they must guess the correct current direction initially. In reality, the assumed direction is just a starting point. If the calculated current turns out negative, that simply means the actual direction is the reverse. The sign is a natural outcome of the math, not a mistake. Second, sign errors happen when identifying voltage rises and drops while traversing resistors and batteries in loops. Remember to carefully track direction relative to current and polarity. For a resistor, voltage drop follows current flow direction, while for a battery, voltage rises or drops depend on whether you move from negative to positive terminal or vice versa. Careful labeling prevents such errors. Third, sometimes students don't identify enough independent loops or junction equations, leaving the system unsolvable or underdetermined. Always ensure the number of independent equations matches the number of unknown currents. This check guarantees that the system can be solved uniquely. Understanding these pitfalls and how to avoid them will make your application of Kirchhoff's rules efficient and error-free. Next, we'll engage with reflection prompts to consolidate your knowledge. We've journeyed through the foundational principles and applications of Kirchhoff's rules today. We started by understanding the necessity of these rules beyond simple resistor combinations, then learned how to label currents and potential differences accurately. The junction rule reflects conservation of electric charge at nodes, while the loop rule embodies energy conservation around circuit loops. Applying these rules to circuits, including complex resistor networks and multi-loop configurations, showed how we can systematically determine currents and voltages even in challenging setups. We also addressed common misconceptions, ensuring you feel confident in applying these rules correctly. With this strong foundation, you're now equipped to analyze a wide range of circuits. Mastery of Kirchhoff's rules is essential as we progress to dynamic circuits involving capacitors and inductors, and later to alternating current AC circuits. These rules also underpin network theorems that simplify analysis of real-world electrical systems. So get ready. The next topics will build on Kirchhoff's rules to deepen your understanding and problem-solving skills in electricity and magnetism. Well done today, and I look forward to our next adventure.